Any questions? Okay, I'll continue with this philosophical discussion about science. Let me start by showing you where the textbook, the course notes are. We are on two course. If you click learning modules, go back. If you click learning modules, we will put here various materials for the course. And the draft textbook is here. For the first month or so, we'll be studying mechanics. So that's in a separate PDF file. Okay. At the moment, we still have last term's file. Since then, we have added a few more problems. We have edited a little bit. On Wednesday, the new version will be available. Hard copies at Canon, and we'll upload the new PDF here. Okay? At the beginning of this is the course chapters, course content list, of course. We have a table of the fundamental constants, just the numbers that we use. You don't have to memorize these things. Okay? We will have here some other symbols. We will also put on the web a glossary, bir özet sözlük, for Turkish equivalents of some technical science terms that we use in the course. In the previous version, these were given in footnotes. We decided to take out all those footnotes, just make one page, which will contain what is the English and what is the Turkish for various concepts, so you can find it in a handy place. Okay. Okay, this is here with arrows is a summary, kind of simple flow chart of how science works. Okay, this you have probably seen before. There's a prediction, hypothesis, öngörü. What will happen if I want to learn about some aspect of nature? Okay. And I have some guess. Under such conditions, this is how the machine works. Okay? Then I design an experiment. Here you have to be clever. What kind of observation, what kind of experiment will give me a way to learn whether this prediction is right or wrong? How can I check that it is not due to some other causes, errors, etc.? So this is an important part of science, how to design the experiments cleverly, and then you test it. If it's verified, just like you write a flow chart for a computer program, come back, test it again. Maybe not me personally, somebody else. Okay? Then you go into a loop in the computer program. You do it again and again, and if it's enough number of times, tested by different methods, different people, but same conditions. Okay? Then you say, well, okay, this is in quotes true. What does that mean? As I tried to explain, it means up to now, in a very large number of times, it has not yet turned out to be false. Which means as true can be. Okay. From this philosophical discussion, you see that there is no better truth than that. Empirically, if you are talking about truth about the world, you learn by looking at it. And if you have seen something the same a very large number of times, that's as much as you can know that it's true. There is still no guarantee that the n+1 time it will not be true. But so far, every scientific or daily life observation that has turned out to be true a very, very large number of times has continued to turn out to be true the next time and the next time and the next time. That's our collective experience of all human culture. That it works the world, we can interact with the world this way. All right? Now, I interpret this word, this sentence, hayat en hakiki mürşit ilimdir, which you have heard, and it's a kind of ritual, and nobody thinks about it. It's sort of has become empty. But if you think about it, I would like to interpret it as en hakiki, means it doesn't say that there are no other truths. It doesn't say that only truth or absolute truth. It's en hakiki, and that's certainly what we can say about the philosophical position of science. It is verifiable, okay, and it is as far as you can go. Something can't be more true than being true in the past and times. You don't know that anything is true before the next time, okay? And another quote that I like to make is something that Galileo is supposed to have said. We will learn about the life of Galileo. We will read about it in this course. Because his life, he essentially laid the foundations of physical science, as well as very consciously developing the scientific method. Philosophers before him, like Francis Bacon, but also before that, even from ancient times, because of this common sense nature of science, okay, East and West all over the world knew about the importance of experience. But Galileo was the person who really laid out that you have to design the experiments, you have to make a control, a comparison. If I do it this way, it happens. If I don't do it this way, if I change this or that condition, how does the result change? Systematic design of experiments. So that's more than a philosophical discussion of the experimental method. Galileo produced the first example, very clear example of designing experiments and using the scientific method. Okay? And as you know, there's this famous story that Galileo was tried by the Inquisition, by the church. This story is sort of complicated because it is not very simple. It's not like, Galileo was a hero and all the people, these religious people and authorities in the church were complete stupid bigots and they were just being against the man, it was unfair and so on. It was more complicated than that. There were people who were really Galileo's enemies for various reasons. There were people who were really bigoted, not just the church, not only for religious reasons, but also for philosophical beliefs, because what he was saying, it was a new way of approaching knowledge, which seemed to contradict, or really contradicted, what ancient authorities, like Aristotle, etc., said. It doesn't also follow either that the earlier philosophers of antiquity, or the medieval philosophers of Christianity or Islam were stupid either. They were also very clever people. But the difference with Galileo was, he was doing experiments, whereas they were thinking, it must be so. And that is also not because these old people were stupid. It was because the possible way of testing for example, measuring time, doing these experiments, was not available. And within their limited experience, the whole discussion of whether the Earth was round or not was possible because it was not yet possible to make a clear designed experiment. So the background to Galileo's being tried is not very simple. It's not black and white. But it is true that he was tried and he was censored. Okay? There were people among the older scholars in the church, among the princes, the political power of the time, who were supporting Galileo, who were his friends. Some of them, for intellectual reasons, they understood what he was trying to do. There were also people of authority in the church, or princes and so on, who were against him. Again, things are complicated. It's not very simple. But there's this famous saying that, first what we know is the sentence, karar, of the church court, the Inquisition, was that Galileo was going to promise not to discuss, not to teach, not to write, etc., his ideas about the solar system and the motion of the Earth. And of course, he was under a lot of pressure. There was a physical pressure. There was a danger of being put under physical torture. I mean, they didn't do it, but there was a threat because they did it to other people. Okay? So he recanted. He said, he signed this document saying, "I'm not going to say these things, teach these things." And then he was put under house arrest. He couldn't leave his home for the rest of his life. But he did have contacts. He wrote and he published, etc. But anyway, the legend, it seems, is that Galileo said, or maybe sort of under his voice, murmured that these famous words, "Eppur si muove." Ne yapayım dönüyor. Whatever I say or you say, the physical world has its own dynamics. It does whatever it does according to laws of nature, not according to what is considered to be correct to say. Right? He probably didn't say it, because to say it, at least to say it loud, would be a very stupid thing. While you are signing it, I signed it, but he wasn't a stupid man. He probably didn't say it. But I looked it up in the Wikipedia, and apparently the first appearance of this legend was some 50 years or so after Galileo's lifetime. But it is nevertheless a very good way of expressing something basic about science. It's exactly like that. And it's not just about the rotation of the Earth or the fact that the Earth moves around the Sun. Whatever it is that you learn about the way the world works is true because that's the way the world works. It's not true because the dominant political or religious or scientific authority or the best textbook says so. Nature doesn't care what you say. It doesn't care whether you believe this or that, or whether you do your experiment right. Okay? And that's what this word, although Galileo probably didn't say it, it's a very, very brief summary of what science is about. We try to, the world is there for us to learn and to enjoy. Okay? And if we are clever, we learn about it systematically. We try to use our knowledge of what we learn with some judgment. Okay? But it's there and it does its thing no matter what we do. No matter what's fashionable. No matter what's allowed. Okay? So these three words, which Galileo probably didn't say it, but could have said it, it represents his whole life of work, and it also represents what science is about. The whole philosophical point of science is. It is there, and it does its things. And there's nothing I can do about it, except learn. Okay? Now, a very important thing about scientific statements is that they are conditional. Conditional in Turkish is şartlı. What happens depends on the conditions, particular conditions there, in principle. For example, if I drop my keys, they fall. This doesn't face much condition. Anything near the surface of the earth always falls towards the earth. So the conditions here are pretty loose. But if I looked at objects falling not on the surface of the earth but on the surface of the moon, they would fall not towards the earth but towards the moon. So that's a different condition. If you now refine, go into more detail about your experiment, for example, you say that something near the surface of the earth will fall. And it will fall down with increasing speed, faster and faster. And the increase of speed, which we call acceleration, is, I have measured it, it's 9.81 meters per second square. Don't worry if you don't understand the units, we'll learn all of this later, but it's something that I measure. And the numerical value in my units is 9.81. True? True. Where? Here, let's say, when I do the experiment. But then we have to realize that if I do the same experiment on top of a mountain and compare the results with sea level, if I do the experiment at different latitudes and then on Earth, the result will be a little bit different. So if I say I measured 9.81, I have to say I'm at this altitude, at this latitude, here I measure this. This is conditional. Okay. So depending on the experiment, there are always things that depend on conditions. The more detailed, the more conditions. The more general, of course, if you go in the direction of generality, it becomes everything near the earth falls towards the earth. This is true. Every two things attract each other by gravity. So if it's near the moon, it will fall towards the moon. But the moon is attracted by earth, etc. That's a more general theory of gravitation. Okay? The validity of that is much, much more general. But there is still a limit. Because if you are studying the motion of objects, you can say, does the way objects move depend on their speed, how fast? Now, people before Galileo, and Galileo himself, and Newton, and all these others, all the classical physicists thought, no. We have certain laws of motion that we learn from experiment, and whether an object is moving this fast, or faster, or slower, or this way or that way, the same laws seem to hold. When two things attract each other by gravity, the sun and a planet, let's say, they move in orbits around each other, and it's always like that. It was only in the 19th century that it was realized there was a condition. Objects that move very fast. Very fast, what does very fast mean? In science, you don't say just very fast, little fast, you know. It's not that loose. You have to say, compared to what fast? Things that move at speeds that are close to the speed of light have somewhat different laws. So the law of motion that you write down about speed, about velocity, about acceleration, depends on depends on what the speed is that you are talking about and how fast it's moving with respect to you. In the 19th century, it was realized from electricity and magnetism and light, it was possible to measure already before the 19th century the speed of light. It seemed that the speed of light is constant. Well, okay. But then, if I measure the speed of light here, and if I put the same experiment on a train platform, and measure it while the train is moving, classically you would think that if somebody moves in a train with velocity 3 meters per second inside the train car, and the train is moving with, I don't know, 10 kilometers per hour, and I measure this guy's speed from this platform, his total speed is 10 kilometers per hour plus 3 meters per second. You just add it. If this is true for light, then I measure light from the train platform, and the train is moving, and the light is moving, light is made with a flash bulb inside the train. I would measure something faster. This kind of experiment was done, and it was found that something very strange is happening. The velocity of light, no matter who measures it, I measure it from here and somebody else measures it from an airplane, they get the same speed. This means the law for adding velocities that Galileo and Newton and everybody else, which makes a lot of sense, just add the velocities, okay, is not true in general. There are exceptions. So let me go on about this law a little bit. So this is how I will write my notes. So here is a train, let's say, and here is someone moving with respect to the train with speed v1, 3 meters per second. Okay? And the train is moving with speed v2. And here is your scientist making some observations, using chronometers, whatever, he's measuring speeds, and observer at station measures V equals V1 plus V2. Right? Any questions about this? This is what you would expect, and of course this is what you expect because this is what you see in all the experiments all the time. Now, consider this experiment. Here is light, speed c with respect to train. And train is going with v2 as before. Okay? So speed of light from ground measured from ground, okay, what do you expect will be, let's say, C prime equals V2 plus C. So this is the scientific method. Based on our previous experiences, I'm making a prediction, a guess. I'm saying, okay, in this case, if the object moving in the train is light, and its speed there is C, the guy outside will see the speed of light as C plus V2. This is my guess. And then the next part of the scientific method, I ask, is this true? How do I ask? I make the guy outside here measure and the answer is no, it is not equal. The person on the platform, instead of measuring C plus V2, measures the same C. Now the experiments for this were done at the end of the 19th century. But even before the experiments were done, Einstein realized this must be like that. The velocity of light must be the same with respect to everybody. The way he realized that was by thinking about or studying the equations, the laws about the electromagnetic fields. Because it was realized at the end of the 19th century that light is just electric and magnetic. It's an electric magnetic thing, we'll learn what it is, that travels. Okay. And the equations that show you how light travels are called Maxwell's equations. We'll learn them in this course. We'll see how they come from experiment. If you put those equations together, you get an equation that light will travel. But the thing that Einstein realized was, from these Maxwell equations, when you put everything, all the experimental results together, in the equations themselves, you get the numerical value of speed of light. It doesn't, the equations don't refer to whether it's on a train or who is measuring is, what is the relative velocity. There is no reference in the equations to the speed of the observer. But nevertheless, from the equations, there comes out the velocity. That means there is a fundamental law of nature that the velocity of light is 300,000 kilometers per second. And that's true with respect to anybody. So Einstein then said that if this is so, our law of adding velocities, V total is V1 plus V2, train plus velocity of the thing inside, is not true for light. If it's not true for light, it means it is not true for everything. So our old knowledge, Newton's laws, Galileo's law of adding velocities, V total equals V1 plus V2, very simple, common sense, must be conditional. It has limits. It is not true for all situations. So he asked that, what situations is it true for? Clearly it must be true for true enough to high enough accuracy. Okay? For all the daily life situations and all the old experiments of mechanics, with trains and cars and airplanes and whatever. Well, what's characteristic of all of those things? They all involve velocities like meters per second, 100 kilometers. At most, in those days there were no supersonic planes, but let's say 1,000 kilometers per hour or whatever. Okay? All of that is very small compared to this magic new velocity, which seems to be constant velocity of light. So Einstein reasoned, now the electromagnetic laws seem to be true. They have a fundamental velocity in them, which doesn't depend on who's observing, what is the speed of the observer, etc. So that must be true. On the other hand, under a very, very large range of conditions, low velocity experiments, trains, cars, bicycles, whatever, are all low, v equals v1 plus v2. That's also seemingly true under those conditions. That's mechanics, all mechanics. So there must be a generalization of mechanics that will allow the old results to be still true, to a good approximation, but also allow for the fact that the speed of light is going to appear as constant for everybody. That was the problem he faced. And everybody has heard of relativity. This is how relativity developed. Einstein realized that there was this paradox, this incompatibility between C as appearing as just one C in electricity and magnetism, and adding velocities which will not give C with respect to everybody if classical mechanics is right. So one of them must go. And he realized that classical mechanics is incomplete. That means it is not unconditionally generally true. It is true at low enough velocities, but not true at large enough velocities. Now, we will go through it again in examples, but the reason I'm telling you is this is a good example of how science proceeds and how something that seemed to be true in general becomes true almost in general, but in a limited conditional range. Now, I will not tell you about relativity in all detail, but I will tell you just what Einstein's formula is. This led Einstein to develop his special theory of relativity, which gives V equals V1 plus V2, just like the old formula. But there is a correction. Düzeltme. Here is the relativistic correction. Divide by 1 plus V1, V2 over C square. Now this is a more general result. It applies under general conditions. It applies under situations where there is light involved or something is moving close to the speed of light. Now we can do many experiments, for example at CERN and other accelerators with particles that are moving not exactly but 80% of the speed of light, and for them we can test that this is true. Okay? Now let us see what this will give us in the case of the light traveling inside the train. In that case, light emitted in train. So V1, the velocity of the thing that's moving in the train, is C. Okay? Let's see what the formula will give. Then C prime is simply, for V1 I'm going to put C plus V1 divided by 1 plus this is V2. V2 is the train's velocity. Okay? 10 kilometers per hour, let's say. Here I have V2 C over C square Right? Let's continue the calculation. Is everybody with me? So, electricity and mechanics problem, Einstein now tries to make a more general theory. And in this theory, he thinks about how time is measured, how distance is measured, how velocity is measured, etc. And this is the new formula. So, C cancels here. And this result, if you continue the algebra, you will find that this is just C. It's a simple formula, not as simple as the old one. But it's not just any simple formula. Einstein deduced it on the basis of making these two different experiments compatible. Okay? So this now gives this a way of adding velocities of things with respect to train, with respect to platform, station, that has the property that if one of the objects is light, its velocity is the same. So it's beautiful. It explains that everything is alright with the equations for light waves propagating, because no matter who measures the light waves, they will get the same velocity, and that formula gives the right result. Now, of course, you could think of other formulas that give you the right result. Okay? But to test if this one is the correct one, they do more experiments, and it is the correct one. Next question is, well, then what's going to happen to Galileo and Newton? Is everything they did, and all of the classical mechanics, which we are still using to design our cars and trains and airplanes and everything, is that wrong? So the next requirement from this new theory is, in appropriate conditions, it should give back the old theory. What are the conditions of the old physics? That trains and guys running in trains and everything else, all those velocities are small compared to the speed of light. So let's now see that. Here slow must mean slow with respect to the reference in this problem, which is the speed of light. So it means, slow means V1 is much less than C. V2 is also much less than C. Okay? For example, V1 is 1% of C and V2 is 1 over 1,000 of C. Then what we have is V is equal to V1 plus V2, 1 plus, well, let me just write here. Okay. A very small number. Right? So it is not exactly equal to V1 plus V2, but it's approximately equal to V1 plus V2. The old theory, classical mechanics, is approximately true when V1 and V2 are small compared to C. So what happened? When it became possible both with theoretical advances, the understanding that electricity and magnetism gives light, and with the possibility of making experiments to test these things, to measure such very high velocities. You need very fine clocks and everything else. Two theories are incompatible, then science makes a generalization. Such generalizations are very rare. I mean, small changes in conditions are addressed by scientists all the time, but something like relativity, the big paradox between two areas of science, take somebody like Einstein, okay? It doesn't happen very often that such a big change takes place. And then, what happened to the old theory now? It is not wrong, but it's approximate. The new theory is now more complete. That means it's valid under a wide range of conditions. But even that, as Einstein soon realized, his special theory of relativity was not a completely general enough theory, because it only gives correct results for things that move at constant speeds. If you want to include things that accelerate, like something falling down, gravity, then Einstein himself realized that this special theory is not enough. He must do something even more general to take account of both gravity and acceleration and things moving at speeds like the speed of light. And then, about 10 years after the special theory of relativity, he developed the general theory of relativity, which is more general. So special theory is again not wrong, but it's not general enough. And the general theory is passing new experimental tests, still going on, but it's now quite solid. But we are not sure that it's absolutely general. In the conditions of present experiments, it's valid. Okay? Okay, so we have had a bit of discussion of relativity and what is theory and so on. You can start by just going into Sukkot, playing around, reading the first few chapters there. Okay, on Wednesday we'll meet again. Okay. If you have any questions, come to me.
Normalde ışık hızını basalım, bunu ekranlarına